Jai Hind students. Now we are going to start about the derivation part of this satellite communication subject, and this equation of the orbit is somehow related to your second unit, and in this individual lecture we are basically going to concentrate on the situation and location of the satellite in the particular orbit. So in the coming lectures, basically we will go through the satellite location in the orbit. Then we should locate the satellite with respect to Earth. Also, we describe the various parameters which are required to locate the satellite into the orbit. After that, we will discuss about the satellite link design. So basically, when we want to start about that orbital mechanics part, actually orbital mechanics is the part of this subject in which you do all the mathematical operations and derivation which are required to locate the satellite into the orbit. So it all started with the Johannes Kepler's law of planetary motion. As I told earlier, that Johannes Kepler gave these law of planetary motion in 1600, and he tells that first law is the orbit of any smaller body about a larger body is always an ellipse with the center of mass of the larger body as one of the two foci. So basically what this first law is saying, that if this is the orbit of the satellite, then it will always be a elliptical path, and the other object which is a larger body that is located on one of the two foci of the ellipse. So this is the first law of planetary motion. The second law, it is about the law of area. So basically this says that the orbit of the smaller body sweep out equal area in equal time. Means if in t time any satellite will cover this area, this much area, it means in the same t time in the another part it will also cover the same area. So this area, this individual law is about the law of area, and this first law is about the law of orbit. And similarly the third law is the square of the period of the revolution of the smaller body about larger body equals a constant multiplied by the third power of the semi-major axis of the orbital ellipse, that is t square directly proportional to the a cube. Means this is the law of period. But you can notice one thing here, Johannes Kepler give these three laws without any type of mathematical expression. So then Isaac Newton came into the picture and he create two law and three law of planetary motion, three law of motion that will help us to derive the orbit of the satellite. So first of all, the law of universal gravitation given by Isaac Newton is, if there are two bodies m1 and m2, then and they are located at a d distance, it means there is a force between these two objects, and that force is directly proportional to the multiplication of the both of the mass and inversely proportional to the square of the distance, where g is the proportionality constant which is introduced to equal this equation, and F is the gravitational force, where g is the gravitational constant which is 6.67 into 10 to the power minus 11 Newton per meter upon Newton meter per kg square. So basically this is about the Newton's gravitational law, and then Isaac Newton give the three law of motion. That three law of motion give the base for the next three equations of the motions. That equation of the motion is different from these three law of motion, and these three law of motion said that the first law state that if no force are acting, a body at rest will remain at rest and a body in motion will remain in motion in a straight line. It means if you are having any body and if that body is in a motion and it will be continuously in a motion if any other till that if any other external force is applied on that body, and if there is no force or is acting on a stationary body, it means there will be no movement in that body, it means that will remain on the rest. Similarly, the second law states that F is equal to ma, means that force is directly proportional to the acceleration and mass here is the constant which is always fixed for that individual object. And third law says that every action there is an equivalent opposite reaction. Basically all three laws are used for your rocket science and that satellite engineering very much, because these all three laws are used for various aspects of the satellite launching and other satellite operations. As if you take this third law, that third law is responsible for the rocket launching, which is responsible for the launching of the satellite into the orbit, because that rocket work on the same principle that when you are filling a balloon with air and just releasing that balloon in the free space, then you can see that the motion of that balloon is just opposite in the airflow. You can see by this diagram, if there is a balloon and if air flow is coming out in this direction, it means there is a equal reaction in the opposite direction and this balloon will move in the upward direction. Similarly, that same rocket, the same concept is used for the rocket launching. Then these three laws, first one was that given by the Kepler's, then the Isaac Newton, these law prepared the basics for the equation of the orbit. How? That you can note here. Basically, when we are talking about the equation of the orbit, actually this is our Earth and that is the elliptical orbit of the satellite in which satellite is moving. So it all started with the Newton's equation of the motion. That Newton's equation of the motion says that S is equal to ut plus half at square. S is the distance, u is the initial velocity, a is the acceleration, t is the time. V is equal to v square. Second equation is v square is equal to u square plus 2at, where v is the final velocity, and v is equal to u plus at, that is the also another equation, and t is equal to ma or f is equal to ma, that is the same as the second law of the law of motion of Newton. So these equations are given us the basic base of this equation of the orbit to derive the equation of the orbit. So here you can see that here I want to tell you one example that whenever in your childhood when you play, then sometimes you just tie a stone with the thread and just move it in the air in the circular motion. You always observe one thing at that time, your stone is continuously moving in the circular orbit as well as its velocity is as equal to required to remain it's in orbit. So it means at the time when you are rotating that stone in that orbit, you actually note one point, a stone is stable in its orbit when the both forces which are acting on that stone are equal. Means at the time of that stone when it is in the circular orbit, two forces are acting. First force that is throwing away that stone out from the orbit, but the another force that is coming from your hand, that is attracting that stone inside that orbit. That's why by balancing these both forces, you are actually maintaining that stone in the orbit. So these two forces are centrifugal and the centripetal force, and here we are talking about that in the F in and F out. So when we are talking about F in basically that is centripetal centrifugal force, and that is F in is equal to G MEM upon R square. It is coming from the Newton's gravitational law. You can easily understand by this that this is Earth and Earth mass is me. This is the satellite which mass is small m. So when, as per the second this formula of gravitational law of universal gravitation, you can see here, if the distance between these 2 points is r, means G MEM upon R square, that is the value of F in. Similarly, we have F out. F out value is coming from the kinetic energy of that individual stone or satellite which is placed in the orbit due to the velocity of that satellite. So you can easily understand one point here. To maintain a satellite in its orbit permanently, two main parameters are required, and that parameters are orbital velocity and height. Here that height is r and the velocity is v. So due to this v velocity, the kinetic energy which is this satellite is having, due to that there is a force, and that force is F out is equal to mv square upon r. So due to that you can calculate the equation of the orbit, and to calculate that orbit you just have to equal out F in is equal to F out, because it is the only condition in which satellite remain its in orbit. So F in is equal to m into mu upon r square, and where actually mu is a new constant which is coming from G into me, because these both constants are having fixed values, because Earth mass is always fixed and G is also G is the gravitational constant. So combinedly it is coming as mu. So F in is equal to m mu upon r square. Similarly, F out is equal to mv square upon r. Now when F in is equal to F out, then by placing all these equation in the equation, we will get a second order differential equation, and its solution will involve 6 orbital element. Means by solving this equation we will get this d square upon r dt square plus r upon r cube mu is equal to 0. This is a second order differential equation which is called also orbital equation, first orbital equation. So when you solve these equation, then you will find out one thing, that you will found 6 individual orbital element. Actually these 6 orbital element are responsible for the satellite location into the orbit. Then this is the about the equation of the orbit. Now you can understand how we derive this equation of the orbit for individual by using this the previous equation. So initially starting, as whenever you want to locate any object anywhere in the space, then you required some kind of coordinate system. So as starting, this coordinate system that is used for the equation of the orbit was Cartesian coordinate system. In the Cartesian coordinate system, you always know that there are 3 points, the 3 axes x, y and z, and you are actually placing the earth on the horizon, and the center of the earth and the horizon is coinciding. So this is the satellite placed here at the r distance from the center of the earth, and if this is the earth, this is the equatorial plane of the earth, which lies in the xy plane, and the rotation of the earth is explained here through this z axis, and the rotation axis is z axis. So basically the initial coordinate system used to describe the relationship between the earth and a satellite, a Cartesian coordinate system with geographical axis of the earth as the principal axis, is the simplest coordinate system, and the origin at the center of the earth, referred as a geocentric coordinate system. So when we are talking about this, then this complete system, when you are placing a satellite, earth on the Cartesian coordinate system, it will become a geocentric coordinate system. So how we are going to calculate this equation of the orbit? So you can see here, actually it is not fixed that satellite will always rotate in the equatorial orbit or in some other orbit. So actually this equation is coming from the satellite orbit of the rotation. So you can here see that in this diagram you are taking another coordinate system. That coordinate system is actually using the orbital plane as the reference plane. Means in this previous geocentric coordinate system, what you are doing? You are just placing the earth on the origin of the Cartesian coordinate system, which is called geocentric coordinate system. The equator of that earth lies in the xy plane, and the rotation of the earth is in the z direction. So this is the first part. Then second is, now you are referring the orbit of the satellite, means now you are taking, that is the z direction of Cartesian coordinate system, this one, and this is showing the earth rotation. But here we are taking satellite orbital plane as the reference plane. Means this is the satellite, and that satellite is having a orbital plane with a angle with the existing equatorial plane of the earth. So a new coordinate system will came into the picture, and that coordinate system having also three axes. That axes are x0, x0, y0, z0. So in the orbital plane coordinate system, in this coordinate system, the orbital plane is used as the reference plane. Means now this orbital plane is used as the reference plane, and the orthogonal axis x0 and y0 lies in the orbital plane. Similarly, in this previous one, xy plane is lying in the equatorial plane. Here these x0 and y0 are lying in the equatorial plane, orbital plane. So the third axis ZO is orthogonal to the x0 and y0 axis to form a right hand coordinate system set, and the z0 axis is not coincident with the earth z axis through the earth north pole unless the orbital plane lies exactly in the earth equatorial plane. Means here you can understand one point, as this satellite orbit is just having a angle with the equator of the earth. That's why the rotation of the rotation axis of this orbital plane is just z0, and which is not coinciding with the z. It will coincide only in the one condition, when the orbital plane is using the same equatorial plane. Then these both rotation axis will be same, z0 is equal to z. So now by using this equation, the last equation, that was this equation, second order differential equation, when we apply this second order differential equation using this geocentric coordinate system and orbital plane coordinate system, then we will get this equation. This equation states that x0 d2 x naught upon dt square plus y naught d2 y naught cap d2 y naught upon dt square plus mu x naught cap plus y naught cap x naught square plus y naught square upon power 3 by 2. So basically this is the simplified equation, that second order differential equation in simplified way by using this equatorial and geocentrical orbital plane system, coordinate system. So now as you see in these all basic previous coordinate system, the main thing is also one point, that is the distance between the center of the earth and the satellite, that is r. You can here see that here r is the fix. In this also this r is here. It means every time you have this r parameter and the angle, you can see that the angle here, this is the angle, that you can easily express the location of the satellite by using the polar coordinate system. So polar coordinate system, you are having a angle phi naught and r naught. So this is the location of the satellite, this is the earth, orbital plane, and that orbital plane, you are here using the orbital plane coordinate system. You are going to convert orbital plane equation into the polar coordinate system, means this one is going to convert into this one. So this is the direction of the rotation of the satellite in the orbital plane. Z naught is the direction just perpendicular to this x naught and y naught. Similarly, you are having the distance r naught and angle between them phi naught. So you can see it in polar coordinate system, you can get these equation, x naught is equal to r naught cos phi naught, y naught is equal to r naught sin phi naught, x cap, and these both are the equation. So by simplifying these equation, you can convert that second order differential equation into the polar coordinates by this equation. This is the second equation of second order equation in the polar coordinate system. So by solving this, we will get the standard mathematical operation equation for the radius with semi-lattice rectum P. Actually, that semi-lattice rectum P is a formula which is coming from the h square upon mu, where h is the height. So r naught is equal to P upon 1 plus e cos phi 0 minus theta 0. Basically theta 0 is the angle with respect to the system, and phi naught is you can see here, this is the phi naught, and that P is the semi-lattice rectum and E is the eccentricity of this orbital path of the satellite. So this will give us the orbital equation of the orbit of the satellite. So in the next lecture, we will discuss the further location and description of the orbit. Till then, thank you.